Alex?
Okay. Can you hear me?
Yes. I mean, in the Zoom, yes. I don't know the hall.
On your screen.
Okay. Should I start? Sorry, cannot hear very well.
We can start.
We can start.
Yep.
Yeah, okay. Okay, thank you very much. My connection, I don't know if it's good, so let me know if there is any problem, okay? Sorry.
Yes, we can start.
Okay. Okay, so I start. Okay, so okay, thank you for the invitation. It's a pity I cannot be there in Corfu, in the beautiful Corfu. Okay, I'm sure you're having a lot of fun, but I couldn't make it. The situation, COVID situation was not very good here in Barcelona, so that was the pity. Okay. My intention here is to talk about the axion mass, okay, and to understand if we can get contribution from the UV physics, okay. So the actual solution to the strong CP problem, of course, is we like it because it's a very neat solution. And now on the top of it is a very interesting thing that, and this is what we claim usually, is that it's fully determined by the infrared physics. Okay, apart from the decay constant of the axion, the rest depends on properties that we can extract from QCD. Okay, and that's what it makes a very predictive theory in the order of getting what is the dark matter abundance, or to understand where we have to look for this axion, okay? So the range of experimental searches, okay? So it's a very crucial, important thing that the axion mass and the physics of the axion is determined mostly from QCD. So we can calculate. Nevertheless, my question here is how robust is this? Or in other way, how easy or difficult is to get the axion mass or contribution to the axion mass from UV physics, okay? Of course, what I want to say, it's easy to give contribution from UV physics. You break the Pacheco symmetry and you get contribution, but here this is not my purpose. Okay, my purpose is to see if there can be contributions without, of course, spoiling the axion solution to the strong CP problem. Okay, and this is what it means. It means that in order not to spoil the strong CP problem, the only source of breaking of the Pacheco symmetry should come from the anomaly, okay? So it means that the only contribution from the action should come from the instantons, okay? So we have to understand if the instanton is dominated by infrared physics or from UV physics, okay? In order to do this, let me recall how it goes, the contribution from the instantons. We'll go back to the calculation of Toft in '76. Okay, let me start with pure Young-Mills. And we can calculate the vacuum to vacuum instanton amplitude, okay, doing it in a semi-classical approximation. Okay, we calculate the instanton, and at the classical level, we get the famous exponential suppression e to the minus 2 pi over alpha strong. Okay, and at next to leading order, we have to integrate over fluctuations around the instantons. Okay, and this is what Toft did in '76. And now is where you get, this is where you get that the contribution comes from integrating over all the instanton sizes, okay, from a small instanton to large instanton. Okay, and the important point here is that this is weighted by exponential factor, but when you include the fluctuation, evaluated at the size of the instanton, of course. The coupling should be evaluated some physical scale. The only physical scale in the problem is the size of the instanton, okay? So this automatically tells you that this integral will be dominated where the alpha strong is the largest, okay, but the suppression is the smallest. And this is, of course, in the case of a Young-Mill theory, in the infrared, okay? So the coupling grows towards the infrared, becomes large there, and now we expect from this calculation that the large instantons, those at the lambda QCD, will dominate this integral, okay? And small instantons, okay, instanton depending on the UV physics, will be highly suppressed, okay? Okay, this is from without including fermion. When you include fermion, of course, we know that the anomaly, the anomalies related with the chiral anomaly, and now in some sense the process we were looking before, the instanton in some sense is a contribution to the chiral breaking. So in some sense now the process is not just the one before, because we are producing now a chiral charge. So in some sense we are producing fermions. Now the process is this one, and now to get a contribution to the vacuum, now we have to close the fermion lines. Of course, we can close them by inserting the mass of the fermions, but now it is clear that on dimensional grounds, this will be proportional to the mass of the whole fermion divided by some scale. And of course, again, the scale, what is the scale? The scale is the scale of the size of the instanton, 1 over the size of the instanton. So for a small instanton, meaning large lambda, again, this is suppressed, okay? So there is two suppression for small instantons, for UV instantons, just coming from these two factors. The coupling is usually in the UV smaller, and now you have to pay a price of masses over the lambda that is related with 1 over the size. Now this automatically also is telling us how we could enhance the UV contributions, okay? What we have to do. Okay, but UV physics could enhance this thing. And it's obvious that the first thing we have to have a theory that tells us that alpha strong is larger than the UV order in order to enhance this factor. And second, it was already realized long ago by Dine and Seiberg that you could, instead of inserting here the mass of the fermion, you could just close the fermion lines with a Higgs. Now here you only pay the price, of course, of the Yukawas. Still is a price to pay, that is a strong suppression, but at least is not so big as inserting the mass of the fermions over the scale, lambda. Okay, so of course, you have to live with this suppression, but at least it's not so big as the other one. So now how to get a simple model where you could have these things? Well, a simple model is to add, for example, extra color scalars let's say at the TeV, okay? We know they don't exist below TeV, but at TeV could be a plenty of a scalar that could change the coupling instead of going down. Let's imagine for a while a model where the coupling becomes frozen, something around the TeV, okay? And now we can estimate the contribution to the instanton amplitude, okay? On dimensional grounds, there will be this factor kappa F that we were saying before is the Yukawa, that product of Yukawas that we cannot avoid. Now there's exponential factor, but now the coupling is the coupling that is not here down here, but much larger. And now, of course, on dimensional grounds, there is if you look for instanton of size for the, let's say, the largest scale, so the smallest instanton, something like m Planck to the 4. So we're getting a factor here of m over m Planck to the 4. Okay, now we can estimate this. This is the amplitude that will give a contribution to the axion mass, square times the decay constant square. And now we can put the factors. We had this kappa factor 10 to the minus 23, the Planck to the 4, 10 to the 72. And now evaluating alpha strong at what we know about the TeV scale or the Z mass, we get a factor 10 to the minus 25. Okay, so in total, we see that in a model like this, we get a contribution to the axion mass that is something like 10 to the 12 square. This is the mass square, so GeV to the 4. Okay, so this is 12 order of magnitude above QCD. Okay, so just a simple model like this looks like, well, you could change a lot the mass of the axion by 12 order of magnitude. Of course, if the coupling, if you don't put, depends on the number of fermions, of course, the coupling could be not frozen, but still coming down, and still you could more or less imagine that the contribution to the axion mass could be sizable, more or larger than the prediction of QCD, that is of order GeV to the 4. Okay, so Of course, why we don't think about this option, I don't know, at least to myself, probably not the others, is because we have to put plenty of scalars, okay? And scalars, we know that it's difficult to keep them light, okay? So the more scalars you put, the more difficult is to solve these hierarchy problems, okay? And so it needs tuning. So in some sense, if you want to solve a tuning that is the strong CP problem, you're facing here another tuning that is to keep the scalars light, okay? Now, of course, you could think about fermions, but now if you put extra fermions, as I want to briefly mention, now you have problems that we were saying with the fermions of the standard model. Now you are producing those extra fermions, you have to close the line, and now you have to get into model building to see if the size is small or not, okay? But I will not enter into this. I also want to mention that there are other options to increase it, okay? That are complicated model building options, but we wanted to understand if there could be a simple way to get this instanton, small instanton contribution to be large, okay, apart from this one that I was saying. We considered with my colleagues the idea of, I don't know, going up into the into high energy, you enter into an extra dimension, okay? We know this can happen, for example, in string theory when you get close to the Planck scale. Okay, if it's open up an extra dimension, we were thinking what could be the contribution. Of course, we know that that there are plenty of Kaluza-Klein state when you enter into the extra dimension. So if the instantons are small in size, what is the contribution that you get there? Okay, now the calculation that we have to do in some sense is straightforward. It's just a repetition of the calculation that Todd did long ago. Okay, we have to integrate over the fluctuations. Okay, now in this case they are the 5-dimensional fluctuations, so integrating over all the Kaluza-Klein. Okay, now the instanton in 5 dimension, we were just because we have to calculate fluctuation around the classical solution. The classical solution we consider in 5 dimension, it was a simple uplifting of 4-dimension instanton. So in an instanton that does not depend on the extra dimension is the 4-dimensional instanton at which we uplifted to an extra dimensions, okay, with the 5th extra components being 0, okay. So this is, of course, a solution of our Jamil's equation in 5D, okay, and now we calculated this fluctuation, okay. Now the calculation, I mean, a priori is straightforward. I mean, we follow the usual process, and now this is the solution. What we get is, so this is what we want to comment. The first thing we get is the famous 2 pi of alpha strong, but now alpha is evaluated at the compactification scale. No, it's not evaluated at the size of the instanton, but now we were getting a factor here, okay, that was interesting, was growing with the size of the extra dimension over the size of the instanton. Okay, so if the instanton becomes smaller than the extra dimension, this is a power law correction. Okay, times a function that we can calculate it. Here is the solution that goes to a constant for large values of R over rho. That goes to a constant like something like 1/3. So this is a third, 3 times the third. So this is more or less a factor 1. Okay, and this plus some log corrections. And this is in content with what we get in 4 dimension. 4 dimension already told you to show that the contribution was nicely resummed by evaluating 2 pi of alpha strong at the size of the instanton. Here we see is evaluated at the compactification scale plus some power law corrections. Okay, and interesting thing is the sign. Okay, surprisingly, we're expecting that the sign had to be positive because in Yang-Mills theories, as I was saying, in 4 dimension, for example, the contribution becomes smaller, the coupling becomes smaller and smaller, as we go to a smaller and smaller instanton. Okay, however, here we see that this is making so the action becomes larger and larger. Okay, alpha becomes smaller here in 4D, so the action is larger, so this exponential suppression becomes more suppressed. Okay, but here we get that the minus sign. So it means that the action as we enter into this extra dimension compensate a little bit the factor 2 pi over alpha strong. Okay, And this is was surprising. We don't understand the sign. It's coming from the calculation, but probably, I don't know, we could have expected a different thing. Now, what does it mean? It means that now if I go to the amplitude contribution of the instanton vacuum to vacuum amplitude contribution, the exponential factor, as I was saying, if I draw this exponential factor as a function of the size of the instanton, 1 over the size of the instanton in GeV, okay, I see that, all the time. Of course, that we were saying the coupling becomes smaller, so the exponential factor become much smaller. But when we enter into the extra dimension, we have this extra power law correction that changes the sign and makes the instanton contribution to increase. Of course, the size of the instanton becomes smaller and smaller, and we enter into the extra dimension. There is a point we have to be careful. 5-dimensional theories are non-renormalizable. There is a UV cutoff. You can estimate it where the loops are important. Okay, so this our semi-classical calculation doesn't make any sense. So we have to stop at some point. Okay, and this is can be estimated to be something like of order 1 over the alpha strong. Okay, so we see that there is a contribution here that you can have when you enter into the extra dimension, but you cannot get too much into it, otherwise you hit the cutoff. Okay, now this is the amplitude contribution, the vacuum amplitude contribution from the instanton, now including the axion. To calculate the axion mass, we just shift, because the axion coupled to the G dual, the axion is shifted by S to the minus A over the decay constant of the axion. Okay, and now we can calculate the contribution to the axion mass. Here the solution, okay. This is the axion mass contribution normalized to the contribution you get from QCD. Okay, this is what we know from QCD, and this is what we usually rely our calculations. And now, of course, we want to see when the contribution is larger than 1. Okay, when this UV instanton, this small size instanton for the compactification scale becomes important, and this is plotted as a function of this compactification scale. Okay. So here, of course, now depends, go back to here, depends how much, you see, this is an integral over all size of instanton, depends how much you get into how much we integrate here, okay? We get too much into the extra dimension, into the extra dimension, we will hit the cutoff, okay? So here are different lines depending how much we integrate over these small instantons. And of course, depending if we get too much into it, we can get, of course, a strongly coupled regime, of course, where the contributions are very large, but you cannot rely this calculation. And we can see that we can still rely if we stay along something like an order of magnitude, probably almost an order of magnitude below the cutoff. And we see that even in the case, if the extra dimension is large, it's close to, I don't know, the Planck scale, still you can get some contribution 2-3 order of magnitude above QCD. Of course, this is as I'm saying, you have to be careful because, of course, we're very close to the cutoff. Okay, of course, if you don't get close to the cutoff, this power law correction cannot be important. Okay, so you have to be a little bit aware that there is this uncertainty that the way we estimated the UV cutoff. Okay, but at least looks like yes, you could do at least in some region where you stay an order of magnitude below this cutoff. Looks like safe, and you could have this contribution to be important enough to give to the axion UV contribution. Okay. Now the situation. So this is the situation just from a flat extra dimension. Sorry, I didn't say that. This is I was considering that UCD enters at the UV into an extra dimension. Okay, and to see what is the instantons contribution when you enter into this extra dimension, flat extra dimension. A more interesting situation that we are considering recently is when this extra dimension is anti-de Sitter. Okay, why is this more interesting? Okay, let me. I don't know how much time I have. Sorry.
You have 7 minutes.
7 minutes. Okay, so in these 7 minutes. Let me recall this situation. Okay, why is more interesting a principle? Just because we know, it's a well-known thing that, okay, so now the situation would be that, okay, you increase the energy and now you open an extra dimension, but this extra dimension is until the sitter, okay? So it's a compactified extra dimension, but the space is not flat, but it's ADS5, okay? This is the metric. Now, it's well known that there is, if you consider correlators of the calculation of the gauge coupling to a gluon on the boundary, in ADS boundary, there is a logarithmic correct contribution, okay? This is a well-known understood from ADS CFT correspondence, okay? Because when you calculate these correlators in the holographic way, you get this logarithm. And this is well-known because the ADS CFT correspondence, the ADS CFT dictionary tells you that the ADS5 throat is equivalent to a CFT, okay? When you have in this throat a gauge theory like QCD, SU3 gauge theory, this is equivalent to have a conformal field theory. Okay, so the physics of this throat is equivalent to a CFT theory that is charged under QCD. Now, of course, if you have a CFT theory charged under QCD, it will contribute to the running of the gauge coupling. Okay, but this is a classical effect. The important thing is here, of course, this is just a completely classical effect. You can calculate from this extra dimension and you get a logarithm. Okay, you can understand it that from the ADS CFT that they should expect, because this behaves exactly as a CFT charged under the QCD. But a priori here in this theory, there are no scalars and there is only gravity, okay? So there is you have this problem we discussed before, that the coupling can grow because you have scalars or fermions that tells you now you have the scalars have to be small or not, okay? So the a priori looks like, oh, we can use this logarithmic enhancement of the coupling for the gluons to enhance the action, the instanton contribution to the action mass. Now, surprisingly, so what we have to look is the instanton in this ADS5 throat. Okay, assuming on the boundary we have the normal instanton. So as a boundary condition, we put the normal instanton contribution in 4D. This is a 4D boundary. But the problem is that we don't find, the only instanton we found in this ADS5 is a cylindrical one, the one that we were discussing before, with no Z dependence, okay? So something like this thing, okay, that extends all the way to in the extra dimension, okay? So what does it mean is when we calculate the action, of course, we have to integrate over the full space, and now you can see the action is going to be much larger, okay? If the action is larger, it means that the exponential factor is going to kill. Okay. In fact, when we calculate this, we see we don't get what we were expecting, 8 pi squared over g squared at the radius of the size of evaluated at the size of the instanton. That is what we were expecting. If the instanton is small and the coupling becomes larger because of the logarithmic factor, this could be a much smaller instanton action contribution. But we get this evaluated again at the compactification scale, okay, at the space where you cut the extra dimension, okay? So this is much larger than what you would expect it, okay? So it seems that this is, although you have this log factor, there is no way to find something. It would be good to find some localized. Question we're looking for is some kind of localized instanton on the UB, okay, that will tell you that you don't have to integrate over all the full space, and you will not have the action to be so much suppressed. Okay, the reason so the question is, we don't know if there were this localized instanton at some point, but we realize that it's difficult, probably it's impossible, because of charge conservation. You can always take slices of 4D slices and calculate the topological charge in these 4 slices, and of course, it's in the instanton, this is 1, and of course, this charge conservation, it tells you that you cannot end the instanton because we will go from charge 1 to charge 0. No, if this at some point this instanton chops here and finish, okay, you'll have charge 1 here, but at some point moving into the extra dimension, you'll have charge 0. So it looks like charge conservation tell you that you cannot have this localized instanton. It should be some kind of cylinder, okay? And this is the reason why, even that look like interesting, it looks like these instantons are also suppressed in this ADS. Let me say here a parenthesis, if I have a few minutes, is that what we found in the way looking for this localized instanton, we found a lot of localized instanton, anti-instanton solutions. Okay, very simple and very nice solutions. I mean, we don't know what to do with this solution. You find a way. I mean, they can be useful. Of course, they don't contribute to the axiom because the charge, instanton, anti-instanton charge is 0. But of course, now we were finding very nice solutions. They were easily obtained by conformal transformation, where you could have an instanton and anti-instanton at the middle of this instanton. Okay, that were extending into the extra dimension, that this is in this direction, and they were annihilating, okay, at some point into the extra dimension. Okay, so there was this nice, very simple solution that we were finding. Of course, this consistent with charge conservation because the charge of instant charge is 0. So in this case, yes, you could have something like localized on the UV boundary, but of course the charge should be 0. Okay, and we found several of these beautiful solutions. You have instanton, anti-instanton, and they get into the bulk and they annihilate there. Okay, but I don't know. We don't know what to do with them. Okay, because for the axiom mass is not important, but I don't know. I just wanted to say if somebody sees some applications of what could be important or interesting. Okay, so let me close this thing and conclude. Okay, so there is the possibility to give, my point was the possibility to give contribution from the UV, but this have to come from a small instanton. You don't want to spoil the strong CP problem solution that the axiom give you. And the only solution you have is to enhance, of course, this small instanton by enhancing the gauge coupling. In an extra dimension, you could do it, but you have to be aware, you have to be very close to the non-perturbative limit to get a contribution to the axiom mass that overcome the QCD contribution. Unsurprisingly, when you go to ADS 5, even it looks like the right place to look for this thing because you have this log enhancement of the coupling, seems to be that this is suppressed. We didn't find a UV localized instanton that could give you an action, a smaller action and a higher contribution to the instanton amplitude. Okay, thank you.
Thank you for last talk and questions. Yeah, please.
Hi, Alex. It's Emilian. Nice talk.
Hi, Emilian.
Do you hear me?
Yes, yes.
Go to the slide where you say the 10 to 12 fourth power is super large.
Sorry, where?
At the beginning, no, just you said that when you put this scalar so small mass to reduce to make a constant behavior of alpha S, alpha strong, then you find a too higher value for there is the transparency in the beginning of your talk, but if you don't find this, no, just a little more, no, some more if you succeed.
Sorry.
There is written 10 to the 12 to the fourth power. There is one which
okay, yeah, here.
Yes. If I understand correctly, you put some scalar at a slow scale in order that alpha S and P does not become large and then with the exponential cut. But so in the scalar and Z, you find too much. If you put the downscale MP, you find too few. So this is a very nice question. Why you don't take an intermediate value in order to find what you want? Maybe too naive.
Sorry, I couldn't understand very well the questions. Sorry, because I don't know if it's my problem or the connection there. Somebody got it. I can.
I think Frank wants to say that to decrease the scale of the Planck.
Repeat, you listen to me or otherwise have a nonsense? You no, you don't listen. Another time, once you will be here, you come to Corfu. I'll go to next question.
Jean-Marie Fer here. I had two questions. The first one is, Mark, you want to introduce, you suggested as an example to introduce an extra scalar, charge scalar. Now there are use extra particles, a little bit like in SUSY, to enforce the convergence of the coupling constants in GUTS. What would be the contribution of those particles? So this is one question. The second one, looking at your extra dimension, and I was wondering, assuming that you take this extra dimension seriously, that means you live in fifth dimensions, wouldn't the theta parameter vanish in 5 dimensions and would then be calculable in the 4D reduction?
Okay, let me first, if I understood well, the first question was if I go to supersymmetric theories.
Supersymmetric theories, any theory when you put extra particles, for example, to ensure the convergence of SU5. We had an example this morning with a 15 and a 35 and so on.
Yeah, you could calculate there, you have extra scalar. The problem is when you have extra fermions. Okay, so if you put extra scalars, there is no problem because there is no anomalies for the scalars. And when you put extra fermion in your theory, I don't know, in this model you have also extra fermions, extra color. Now you have to be careful because the instanton contribution is a contribution that also produces these extra fermions. The fermions have anomaly, okay, chiral anomaly, and there is a contribution, the instanton contribution gives you. So you have to close the line of those of the fermions, and now you enter. I don't know. You have now, when you have fermions, the situation is a little bit more complicated. More complicated. You have to close the fermion lines because the process of the instanton produces these fermions. Okay, this is the famous top vertex. So I don't know in those cases if you have also extra color fermions, you have to do this calculation. So I don't know.
Like fermions.
Okay, the second question you were asking, you are completely right. You go to extra dimensions. There is no theta problem. The theta coupling that you can put in extra dimension. However, it has to be compactified, the extra dimensions. And now, sorry, I went probably too fast. The situation we consider here is an orbifold, so 2 boundaries. And now on the boundary, you can put a theta term. So is it true that you in the bulk, you cannot put it, but you can put it on the boundaries, okay, of this extra dimension. So you have the problem, the theta problem is still there. Yeah. You see, you cannot avoid it. So
does that mean it becomes calculable or you still put it back?
No, it's not calculable because on the boundaries you can put anything. A theta is a free parameter on the boundary. It's like because the boundary is 4 dimensions, so it's like normal theta.
Suppose it to be 0 on the boundary.
Sorry?
Could impose it to be 0 on the boundary.
No, a priori it's not 0. You don't have an axiom. Of course, you have an axiom, yes, it's 0, and now you have the axiom. But if not, you have a theta. Is it possible to put it on the boundaries?
Alex, I had a question. This linear dependence of the action in the floods case, is it can we interpret it as the running of couplings from the 1 over rho to lambda, or is different?
It is different. I mean, no, you can. Yes, yeah. Thanks, Emilia. You can, of course, you could expect this because already the coupling, as you're calculating long ago, gets correction of that grows with the radius, okay? When you enter into the radius, into the extra dimensions, okay? So you could expect this power law. However, I cannot resum this thing into like we were doing in 4D, like something like this, evaluate it at the rho, no. Surprisingly, of course, because even the sign is wrong. So I cannot reabsorb it. I would expect if I enter into the extra, if you look at your calculation, when you enter into the extra dimension, non-abelian theory give you a positive sign. Okay, so we got the sign is negative here. Okay, so it's not possible to be resummed. Yeah, I don't know if there's something better to understood. We thought about this, but the calculation is the calculation. Seems to be that you get this result. Yes. So you expect the power law, but you cannot reabsorb it to say, oh, this is the coupling, including the power law that you will get it at some scale like this, at some scale rho, when the instanton size is smaller than the.
Okay, thank you. Thank you.
I also have a question, Alex. This is Nick Mavromatos. Very, very nice talk. On your solution between instanton and the instanton, what is the contribution to the energy density of the vacuum from such solutions? Because if it is non-zero or time dependent, they could contribute to the vacuum energy density if you put this in a cosmological setting, or it is zero.
The action is this. The action is this one.
Right.
So the action is very simple. First, because it's localized, is what you expect. Is a priori is not 80 pi square, it's 16 pi square because you have an instanton, anti-instanton. So it's a contribution to the action is twice. Okay, but you get, so it's 16 pi square over g square. Now, yes, the coupling evaluated at the size of the instanton, you see, because it's the difference between the having it localized or not localized. So because now the coupling at the small instanton grows because of this famous logarithmic factor that you have in ADS. This size, the action could be much smaller. So the amplitude, the contribution to the amplitude could be much larger. Yes, I don't know what could be interesting for this thing. I don't know. Yeah, energy
density in the vacuum, for instance, some contributions, or some dark energy density if there is non-trivial contribution on the four-dimensional.
Well, a priori, this is, I call it energy density, but of course this is the action because
but I'm saying whether this can contribute an energy density on the four dimension when you project things. That's what my question, because that could contribute to the dark sector nicely. I don't know.
But there could be a contribution to an amplitude. This is not.
That's right. No, I know. So that's my question. Probably it wouldn't affect the dark sector. That's my question. Whether
no. But your question is interesting to know if there are objects like this, soliton of this type of other that contributes really to the energy. Yeah,
that's right.
Yes, you're right. This could be an interesting thing. We were thinking to see.
Thank you.
Thanks for again. Let's go to next speaker. Our next speaker is the Epicurus Clafitis.
Just a second. Okay, thank you. Let me see. Go out.
Stop screen sharing.
Hello.
Alex, thank you.
35 minutes, you give me coordinates, right? Thanks for that. Yeah. Okay. Can I stop? Let me see if I can go back and forth. Right. So I'm going to give going to discuss an idea that bothers me, let's say, me and my PhD students for quite some time, is the possibility whether you can geometrize not the cosmos, but the microcosmos on a supermanifold using methods of differential geometry. And as you can see, and some of the ideas here was based on these papers, and some of the papers, the recent work that I'm going to emphasize is the inclusion of fermions in this setup. Right, so let's see. So the first thing is I will give some preliminary, some motivation for that. And I hope that will be proceedings. That's very important. And it's good to the organizers, actually, I like to thank that produce proceedings for this conference. Then I will discuss about gravity variance in ground of gravity. Then I will discuss what the problem is. There was a problem that stopped this program compared to all other problems of geometrization, like string theory and other programs like the amplitude hadron and so on. And I try to convince you that you may well live, whether we can live with a supermanifold. I will try to see what the problem is and try to give present the grand covariant effective action, including fermions. Right, so let me start giving some motivation. I'm not going to go through all that. The only thing is just geometrizing the cosmos. It was actually many civilizations thought about that, tried to formalize in a more civil setting by Pythagoras and tried to put in the form of Platonic solids that our cosmos should be geometrized, not only the cosmos, the stars, the planets, but even there will be also the musical universalis and having some harmony compared to. So these ideas, of course, this developed. Okay, so what I'd like to show you here is how we go from cosmos to microcosmos. This idea was then later came into the debate between geocentric versus heliocentric system. Okay, and as you can see from Anaximander and Tycho, which is an hybrid system. Okay, and the heliocentric system with Copernicus, of course, who have the rigorous, so the explicit analysis of the heliocentric system. And finally, as we know now that both the Tycho's model and the model with the heliocentric is just a problem of choice of frames. One is a non-inertial frame, the other is an inertial frame. It will include fictitious forces, we describe the cosmos. And finally, we had later the debate between the absolute and versus the relative local inertial frame gravitation. And this came to the conclusion again that you can have more freedom and using diffeomorphisms, okay, the symmetries of diffeomorphisms, and you can write even the microcosmos in a diffeomorphic invariant way and solve this kind of frame problem. Still, we still have some geometrization problems with the microcosmos, and this come from the quantum field theory and quantum gravity. We are living now in another age, which is the age of quantum physics. Right, so this geometrization was very important, I would like to say, and again, the importance was demonstrated here. Actually, I went once to the office of the church, and I want to ask something. I say, okay, I would like to ask a question. Okay, and then immediately replied to me, no one ignorant of geometry should ever never dare to enter this place. Okay, so I said, okay, this is actually it says a geometric cosmodicity, which means exactly that. And this is exactly, of course, this is a writing from Plato, and this is actually the Plato's Academy before closed down by the theocratic system at the time. That was exactly what is inscribed there. And that's what I must suggest you, I would say, this beautiful Corfu series, to put that kind of sign, which actually here we had, as I said, a lot of discussions. Everybody uses some symmetries, geometric text, context in text of string theory, and so on. Everybody is looking and striving to understand the cosmos along the lines, okay, more or less. So let me see how, so the approach that I'm going to discuss, okay, let me first show what the problem is before we are going to how we will solve that. So the first one is that we have to the old problem or recent problem within the quantum physics, whether the Einstein frame and the Jordan frame are equivalent formulations of quantum gravity. And of course, in the classical case, there is no problem. You can go from the Jordan frame to Einstein frame by making a field reparametrization. Okay, you can go in field reparametrization, you can have that. But when you quantize the theory, okay, the same reparametrization you have done to go from one action to another does not work. Okay, you don't get automatically that the same parameterization of the background fields does not work, So the effective action is state dependent except at extremer reaction. Of course, this means you are calculating the S matrix amplitude, you are in particular extremer, or then you don't have, may not have this problem, but sometimes you need to calculate effective field theories, as we have seen in some talks. In this case, you have to worry about this frame dependence. You have to go calculate the delta rho electroweak observables, which are also offset quantities, which you also have to worry about frame dependence. And there is a big list, actually. You'd like to calculate bright bigness, resonances, which you need offset correlation functions. And last but not least, you need to calculate the inflationary potential at the quantum level, which also is frame dependent. So this is a partial list of reference, and this idea of the Mach's principle and device transformation of units. This is the context of this framework of this scalar tensor theory. It was from 1962, and there were a lot of papers, and I believe also that it works groups by Steinmetz discuss the question of quantum equivalence between the Jordan frame and the Einstein frame. And I believe we try to give now a solution to that using a covariant formula similar to the Einstein without assuming any new symmetries, no new particles, and no new extra dimension. We like to see how far we can go with these differential geometric methods. And if there is a need, we can include them. So this idea at the action level, at the path integral level, was discussed first by Wilkowski and Dubik, but it was before by other people at the amplitude level, by Gaillard, and I think by Honecker. Okay, in the non-supersymmetric case, and Luis Alvarez, Gomez, Friedman, and another collaborator, I don't remember the moment, in a case of in supersymmetric theories. Right. So, so as you can see, there was a big gap, and there are very, very few. The beginning was a lot, but there are very few papers in between. I can't list all the groups here. And you can see now that the idea is to have a classical action. You have model functions. That means here you can have f of phi, r. This is the kinetic term. I put it in the covariant form because the space-time might be cut, and v of phi does the potential. So this is the model functions, which you like to see how they respond under transformations. So granted, the covariants are interchangeable in my discussion here. And of course, you know from Einstein that you could have, so this action should be space-time deformity invariant, which means that the line elements should be invariant with coordinate transformations. And there is a second also a condition, I would say, or a condition that a property that the action should satisfy, that it should be invariant under field reparametrization, because you like the physics to be covariant, to be the same, and that means you can have a graviton in principle to depend on another graviton and for scalar field, but with the overall factor, and a scalar field will only depend on the other fields phi. Here we don't assume there are derivatives, so all these transformations are regular functions and local. Right, so, and you may ask the question, okay, what do we learn after 40 years of development? Okay, so what we learned from that is exactly this. That these two transformations are not compatible with one another. Okay, that's exactly the observation. You can see here, if I do this omega squared phi, this field here, this line element, without transforming the coordinates, without the tildes here, then this line element violates is not the same. Okay, and there is no why diffeomorphism and before transformation do not. So what we should do? So that means there is an anomaly here, and the way to do that, we have to produce a new model function. That's what we did actually in 220. And the line element, the right element, should be G mu times L square phi. You could think about other things, becomes more complicated, but it should be a kind of measure that could divide out. and this dependence on the conformal transformation. So you can see all the model functions. Actually, the last three has been reported before in the literature, and this is the one which we included here. So the frame invariance of the classical action has exactly that form, and you can see that L should also be included in this action. However, why without worrying about that in all this calculation? Because we can reparticularize L equal to 1, and you don't need to worry about that. But by changing the F case and the tilde, by changing the other model functions. But the path integral, you have the path integral measure. There is nothing there to absorb it. Okay, so there is an anomaly here, which will strike it back at one loop level, and there is nothing to absorb it, and that's exactly the reason why this function is important. So if you go to this Jordan, an Einstein frame, and you work with Einstein frame with canonical fields, what we should assume that in the Jordan frame there is an L with this particular form, so that the Einstein frame is 1. So there are some extra complication which we ignore. As long as we stay at the tree level, there is no problem. But if you go beyond the classical approximation, there is an anomaly. And of course, this anomaly was discussed by other people, by K. Falls and calculationally. But here we like to put a formulation, a formalist, because this is. Actually, I have to go faster. I thought you give me the same time when the previous speaker had, because of the previous. Okay, so. Right, so the point is now we have this metric which we can construct from the effective action. Okay, this is the metric, the field space metric, for the graviton, not the graviton itself. So you have to think first that the coordinates of the ground configuration space are the coordinates, the fields themselves are the coordinates. Okay, and this I use the Width notation, and you can calculate the metric. I think we are wrong. Sorry. I have the 10. I think we are wrong. Sorry. In the time. Right. So the conditions now on the inverse metric is that you can have now the metric, and you can see that the metric you can have the inverse metric, which is produced through using the metric fields, and if you equate them, you find that this gauge fixing term can take two values, 0 and 1, and the 1 is the value which is used by Wilkowiski. Okay, anyway, so this is our details. So the important point here, how do I calculate the Coulomb effective action? The Coulomb effective action has this form here in the standard textbook, so you can see here what is wrong. So this equation, as you can see, we use it, is not correct. Right, so it's not invariant under frame transformation. So if you like to use an effective action that is compatible with the homomorphism, with gravity covariance, we have to make sure that this here, this chart coordinate is invariant. And what you see here is that we need to promote that to a vector. And that's exactly what Wilkowiski did and Stakely did. So they had to promote that to a vector where the one field phi. When they transform the field phi, the chart phi, this becomes like a vector, transformed like a vector. Whereas it's a scalar with respect to the path integral variable. Here I have both the graviton and the scalar field, and there is a compact notation of the width, where some indexes means summation and integration all the time. It's very compact notation. Well, as you can see here, the integral measure has a very explicit representation, which we found, and if possible, you can also work out the volume factor, the volume determinant from the, volume factor for the major form of determinant, and this is nicely done in 1987 for SUN theories and 80 for SUN theories. But the SUN theories do not include gravity in that paper. Okay, here we include everything. Right, so I will not discuss. So here I'll just give you an idea of how the effective action looks like. We have a determinant, which is this bar, which means you have to include this model function. Okay, it's different. So long as the determinant is okay, trace of logarithm. And you can see here the one index is covariant, other is covariant. So this effective action, which is written explicitly, are covariant. And not only that, you find a relation, an equality that the effective action phi L of K B is invariant. Okay, and the Frame transformation transforms has this beautiful property. And the frame problem we had before, you can solve as long as you can deal with that to allow this perturbation theory. I mean, this is just perturbed one loop, but this is a general result of effective action. Right, so let me go to the Fermi problem for my last 10 minutes. So then the Fermi problem is the question whether we need or not on a supermanifold. This was a tough problem. And this is just to flash from 84. And when we discussed that, first discussed how unique that is. And it's clear that in order to have a metric, like a scalar metric, you need two derivatives. But if you have formulas, we have just one derivative. So it says that the metric here should be determined by the highest derivative in the superclassical field equation. This cannot be correct in the Fermion sector or supergravity theory. Actually, not in supergravity for any theory, where the highest order derivative is first order. In other words, you cannot make a fermionic metric just because you have just one single derivative. I mean, you can have here a Poisson vector, but on the other side, we have a chart coordinate. So this is not easy to build. And this is recognized. And by that fact, it was clear that all this program was only discussed within the context of scalar theories for inflation, and they try to see that the fermions should not transform. And here it says, although I cannot give a general way for the metrics, I believe that we also give, of course, is effectively unique, not so effectively unique, only once you include the model function. Right, so let's go how to do it in a super manifold, how this can be done. So you have here a ground field space manifold, so you have a coordinate, you have scalar fields and fermions. And then you can see that this is just a multiplet, okay? This is just the scalar fields and the fermions in 4 dimensions, if you like. What I like to convince you is that the Lagrangian, which has the right properties, is fairly covariant of scalar fields and fermions, should be written or can be written always in this form. So if you use this multiplet, one that contains the two derivatives, which is the scalar, and this will play the role, or it was playing the role of the metric in the bosonic theories, and one that has one single derivative, and I have not phi, psi, but I promote it to a vector that it has the properties of a proper vector. So I try to do what we did, Bilkovitsky did for the source inside the Lagrangian, and this takes more time. So it was a much harder task. And this is here is a generalized potential. Right, so let me see how this works. So I'm just giving you some idea. I'm not going to go through all that we really can construct. The K and B is just two derivatives, left and right. So you have to be careful here. You are in a super manifold. They are not commutative. You have to learn all the mathematics for super manifolds, left and right derivatives, and we have left and right indices, and this is really quite dense. So you have to be careful of the position, how this objects act. You can subtract that and you can still obtain this vector. And if you now try to go to a free field theory to see how this formally compares, you can see that for a free field, so this is scalar fields, that's the scalar mass, that's the Fermion kinetic term. You can see you can write a model function for the kinetic term, which is this one, and the sum zeta mu a. Right, so you can have an algorithm to relieve the gamma mu, and then you can calculate from there, you can derive, in other words, a rank 1 field space tensor, open field space tensor. Then you can go left and right, so you can use an analogy from QFT, so you have like form 2 super form, differential form, and you can produce a rank-2 tensor, a proper rank-2 tensor by this operation. Notice here, this is just ordinary derivatives, and the affine connections we need will cancel out. Okay, this super symmetric, anti-supersymmetric, the lambda, it is anti-supersymmetric. That means under super transformation change sign, and that's the form of that. But even though it looks super symmetric for you, it's not supersymmetric, it's anti-supersymmetric. Okay, right, so, right, what kind of properties this metric should have? First, it has to be uniquely determined from the action, as we did. Transform as an active field space tensor, if you like to promote something like a metric, which exactly we did. It has to be supersymmetric, should not confuse with supersymmetry. I'm not using supersymmetry, I'm saying that we already live in a supermanifold. That's the claim here. Okay, and the fermionic degrees of freedom make our field space supermanifold supersymmetric and not similar to produce a non-zero line element. Should be ultra local, should not have derivatives, it should depend, that means should not depend on derivatives like that. Have the form, this form here, and so on. Okay, so then you can determine the full line of this in this field space. So you demand this form, which I have here, to be universal. Okay, should be local. Okay, it has to be local. In other words, the metric of this field space metric should be this form here. This is the corresponding atom mu, for example, in general relativity. Okay, that's exactly the form we like to have. And knowing the lambda AB, knowing the local form, you can find the field lines and you can construct the ground field space metric. This is the ground field space metric. You can calculate Christoffel symbols, you can calculate the Riemann tensor. You look at that, you have to be very, very careful with the indices, beta and gamma, and all that. You have to be careful with the grading of this Berezenian space. So this is already known in the mathematics. The only thing I like to, thank you. That's my final part, yeah. So you can now construct the effective action both for scalars and fermions. So here we have the path integral measure where phi q includes the gravitons, scalars, and fermions. Okay, could include, in that case here we have only scalars and fermions, we only mind the graviton. So this is the super determinant of G, of the metric, of the field space metric. So this is the action, and you see the source. How now, if you like to generalize that, it has to act right in this way. Right, so you can calculate, this is a non-perturbative result, all orders. You can go to one or two loop case, you can expand that, you can see that at one loop level, you get now the logarithm of the super determinant, which is equal to the super trace of the logarithm. That's what the super trace techniques, which discussed by Debes yesterday, and it's applicable for SMET. But you can go beyond the one loop level, a two loop level, but you have to be very, very careful with the indices, the position, the fact that you have two flame covariant propagators, both on left-hand side, left and right. These are different propagators, but covariant. Both of them are covariant, okay? They are transforming, have the right transformation properties, and you can see all the indices are contracted, and what you see here, this is a fully ground covariant effective action. Ground means both field space and coordinate space. Okay, that means covariant for space-time we already knew, but now we have a complete description both for scalars and fermions. So let's take a simple fermion model, and you like if somebody gives you this model, immediately you say it's not normalizable. But if you calculate the metric and calculate the Riemann tensor, you find that the space is flat. So somebody can play a game with you, okay? Something you cannot see if you don't have this formality. Just like to show you this formality is just not formality, but somebody could come with that module, okay? And you can say, oh, this is normalized performance because it has these high-dimensional operators. Oh, there you can see that the space is flat, and that means there is a parameterization to make it. In fact, there is a parameterization, is you need to think a little bit how not too hard, but you can find it in this case with a single fermion. That's a model with a single fermion, and you can find it. You say it's canonical. If you ignore the Yukawa and the potential, this is a free kinetic term, and you can calculate the ground effective potential action up to one loop level, and you can see there's a kind of super trace type form here, and you get extra contributions actually, which might be interesting for people doing effective field theories with 5 fermions. This form was discussed in Zen Houston, I should say, in this textbook in the very last edition, okay, which was 5-6 years ago. Right, so if you have multiple fermions, again, you can have this kind of form. You can say, okay, what kind of models this theory will generate? We can take the scalar, the real one, and we will have the, something like the vector psi mu gamma mu, du phi, and all this stuff. Okay, so this thing here, we don't know whether this theory could be reparametrized to canonical theory or not. At least we have a formalism. At least we know the geometry of the space, and we have really, you calculate the metric as we do it here, for when we put that to 0, and you calculate the Riemann tensor, the super Riemann tensor. So the super Riemann tensor has a non-zero curvature. We have not been able to calculate much because the complication of this calculation with all this psi of psi, this is a vector, is really enormous, and we have to teach mathematical new rules, which has not been included, or at least I didn't do that, but my students spend a lot of time, which is not humanly possible to do it by hand. Okay, so that's my conclusions. Right, so the conclusions is the first one is reformulation of the ground invariant axiom for scalar tensor theories with a complete set of model functions. This means that there is a new model function that determines the uniqueness. That's a question was asked in 84 by DeWitt of the VDW path integral measure, especially from the gravitational sector. And the line element should have exactly that form, so that both the line element and the effective action is invariant. So there is, we derive rigorous algorithms for calculating the field space metric from the classical action for both bosons and fermions. The extension of the Vygotsky-DeWitt formulas on supermanifolds, so in order to include fermions, we need to extend the VW formulas on supermanifolds. We have to geometrize on a supermanifold necessarily. And this opens the portal to discuss, or at least the chance, the opportunity, a great opportunity to discuss realistic theories such as the standard model. Okay? And finally, we have derived the ground invariant actions from the fermion. So the bottom line is, of this discussion is, yes, we may already live on a supermanifold, and that's the line element of field space metric. And this still we need to do work to substantiate this claim, but for the moment you can take it as a conjecture. Okay, thank you for your attendance.
Thank you. Questions, comments? We are calculating the effective action. Could we say that capital phi bold is an analog for Faddeev-Popov ghost particle, or is it a completely other thing?
No, the Faddeev-Popov action is when we try to calculate gauge theories. You have to include non-abelian gauge fields. You need to first, okay, this action was popular because you had the possibility at that time to, by geometrizing, to go to a particular gauge, which is called the Landau-DeWitt gauge. And whenever you have because you have a PRS symmetry, so the model functions or whatever become, for this line element, that symmetries become isometries. So that means whatever you have away from this geometrized Landau-DeWitt action gets projected out. You can project out. And this is a beautiful thing because now we have a geometric way to write down a gauge invariant effective action. That was the beauty of that, and that really was pursued. But I'm not done with that. I'm trying to include the fermions. I like to see also the anomalies in the graviton sector from the line element, okay? Oops, from this one.
In the beginning of your talk, you asked the question about equivalence between the two frames, in which the Jordan frame and the Einstein frame. Did you finally were able with your formula to see easily that the two frames are equivalent on cell, or
this is two frames are equivalent completely, and I believe this problem has been solved now because of this formula.
Now, a related question is that we start from a first order formalism of gravity, in which the convection and the tetrad are independent variables, and then you solve one with the other with the equations of motion.
I do not do this one, and I don't know. You need to do.
Is that pure gravity, the two formulas are equivalent, but once you have scalars, as you studied, the two theories are not equivalent. I think it would be interesting to apply your method to study this first order formalism.
Yes, I agree here. I just had the typical, the traditional, minimal Einstein action. So whatever I cannot make differential geometric any theory. For example, if I have C square or R mu, I don't know how to do that. So this should come out from radiative corrections. Okay, so it's not any theory. It's only for this class of scalar tensor theories. And actually, for that, just to give an illustration, because I have a backup slide. In this field space configuration, the Riemann tensor for the graviton only, this is this thing, okay? It's quite big and just in 2020. So, and you can calculate the Ricci, this is the Ricci tensor in field space, and the Ricci scalar, which you see is negative. So, of course, you need to do that with that kind of formalism and include it with a bigger frame. And it might give you further freedom, as you say, to include bigger classes. I don't know with this first order formulas in this program. But this frame problem, which was in the quantum world, from my point of view, I believe this formula has been solved. It can be solved in this way.
Let's thank the speaker again. Let's speaker question. Yeah, okay. Thank you. Good afternoon. My name is Zoltán Trócsányi, and I'm honestly grateful for the invitation to this nice place because I can talk to people, I can swim in the sea, and also we have nice talks, and I can give this one, which was done in collaboration with postdocs and students. And I'm going to report a condensed summary of these papers. So actually, I was hoping to give the first half of this talk a year ago, but for obvious reasons, it was not possible. Therefore, I have to present two talks in one, which means that I will have to squeeze in many things. And
it will be very suppressed. I'm happy to talk on details. And then let me give you my motivations to this kind of studies. And I want to recall very nice talks by experimentalist colleagues. In particular, the messages that I take from those talks is that the standard model describes final states of particle collisions at colliders very precisely. This is a very important message. And the other important piece is that there is no proven sign of new physics beyond standard model at colliders. This may seem negative, but actually you can also take it as a positive result, so that we know for sure that at the LHC or up to the LHC, the standard model works very well. And we also know, on the other hand, that the standard model vacuum is metastable, and it means that the potential becomes unbounded from below at energies around 10 to the 11th GeV. And well, this may you take seriously or may not, but it's a warning sign that there is some problem with the standard model if you want to take it seriously up to the Planck scale. If you go beyond colliders, we have very firm observations from the cosmic and intensity frontiers. We know that there is cold dark matter which fills the universe. We also know that neutrino flavors oscillate, which means that neutrinos must have masses. And strictly speaking, the standard model is does not take into account the neutrino masses. Then we also know that we are here to give and listen to this talk, which means that there is a baryon asymmetry which cannot be explained by the CP asymmetry in the standard model. Finally, there is very strong motivation that there was inflation at the early universe, and we know for sure that there is accelerated expansion of the present universe. These are all known facts, and you can find them, for instance, in PDG. So what I'm trying to propose is to try to explain these with as little extension of the standard model as possible. What sort of extension can it be? Well, obviously, neutrinos must play a key role because they have non-zero masses. Therefore, they must feel another force apart from the weak one. And that could be, obviously, Yukawa coupling to a scalar or more scalars. And that requires the existence of right-handed neutrinos. The simplest extension along the logic of the standard model, which is based on a gauge group, well known, is to extend it by a new U1. And of course, many people have put forward and studied such extensions. What I'm trying to emphasize here is to do it exactly the way as the standard model is built, that is, it's a renormalizable gauge theory without any other assumption, any other symmetry. And we can fix the charges of this new gauge group by requirement of gauge and gravity anomaly cancellation and requiring gauge invariant Yukawa terms, allowing all possible gauge invariant Yukawa terms for the neutrino mass generation. So what is the particle content in the standard model? You are all familiar with this picture. We have this layer structure, the strong force on the top, then the electromagnetic force and the weak nuclear force on the bottom, and the quarks and the leptons are arranged in the family, in the three families. We have the mediators of the forces, and we have this Higgs scalar, which is in contact with everything. And what I'm proposing here is to put yet another layer exactly along these lines below. So the fourth layer contains three right-handed neutrinos in the three families, an extra Z prime, and an extra scalar. So it is, if you like, this is the message that you can take home. This very simple, very economic, and probably useful extension of the standard model. The next slide is the advertisement. So with this, I hope to explain the Dirac and Majorana neutrino mass terms. We have some paper on that. Then the lightest new particle is a natural candidate for Wimbark method if it is sufficiently stable, and we have a paper on that. We know that there is CP, well, not for sure, but there is strong indication that there is a large CP violation in the neutrino sector, which can be the source of leptobaryogenesis, and we are investigating this. We have a second scalar, and together with the well-known BH field, it may be the source of accelerated expansion of the universe now and inflation in the early universe. We had some paper on that, and we are also continuing investigations. And therefore, this all motivates me at least, but I hope to motivate other people, is that extensive phenomenological studies are required and useful to confront predictions of the model with measurements and decide whether or not these promises are fulfilled. Now, I'm going to spend very little time on the particle model. This is the new added to the standard model fields, the three right-handed neutrinos. We have the U1 part, which gives an extra term in the covariant derivative, just like the other U1, with different coupling and different charges and different field. And the new U1 kinetic term includes also a kinetic mixing. So all these has been put forward before. This new scalar is a scalar complex singlet, which appears in the scalar potential, and the scalar potential is just quadratic quartic pieces and also a quartic piece which mixes the two scalars, the phi and the chi. After spontaneous symmetry breaking to the observed SU3 color and U1 electromagnetic, we have scalar fields and corresponding Goldstone fields in arc psi gauge. So all this is very standard. Then in the Fermion scalar sector, we have the standard Yukawa terms, and we assume neutrino Yukawa terms, which can be either Majorana type or Dirac type. And in order that these gauge invariant, we need a relation between the Z charges of the right-handed Majorana, right-handed neutrino fields and the new scalar. So these lead to Majorana and Dirac mass terms after spontaneous symmetry breaking. But before I jump to that, let me just discuss the charge assignment. So there is a almost 20-year-old paper which studies that such U1 extensions, in such U1 extensions, the anomaly cancellation means that we can give the extra charge, Z charges in terms of two real numbers, Z1 and Z2. And in this model, I assume that the Z charges of the left-handed electrons and the right-handed ones are opposite, equal but opposite. This is an ad hoc assumption, if you like. And then a gauge invariant and normalization condition gives these charges fixed. I mean, these are fixed up to an overall normalization, which can be absorbed in the Z coupling. It is amusing, but I'm not sure whether it is very useful that with the reparametrization of the couplings, these new charges can be assigned only to the right-handed fields and the scalars. Now, these are the neutrino mass terms, Majorana and Dirac type, which appear in a 6x6 mass matrix in the usual form. And in order to, I mean, strictly speaking, it means that the left-handed neutrinos are massless, but of course, the left and right-handed neutrinos have the same quantum numbers, so they can mix, and this kind of mass matrix leads to type 1 seesaw, which is also well studied. This means that in this model, the Dirac and Majorana mass terms appear already at 3 level by spontaneous symmetry breaking, so it is not generated radiatively, as studied in the literature. Now, we have to diagonalize by a 6x6 unitary matrix from the flavor eigenstates to the mass eigenstates. And this is also well known. These blocks are semi-unitary, and there are many useful relations collected in the appendix of our paper, but I don't want to go to the details. The full diagonalization is actually quite cumbersome, and one can use the seesaw limit to perform an approximate diagonalization in this form, where I can compute this product and obtain this approximate form where in the off-diagonal and also in the heavy part, I neglected terms which are small in the seesaw limit. This UAS matrix is well defined in terms of the Dirac and Majorana matrices, and this is what we call the active sterile mixing matrix. At this point, this MN, which is almost MR, is already diagonal, but M nu, the light mass matrix, is not yet so, which can be diagonalized with U2, and essentially you can identify the U2 with the Pontecorvo-Matisakata matrix, with the PMNS matrix. Now, we have experimental constraints on the upper limits of the elements of the light neutrino mass matrix. And even if at 3 level those are satisfied, the loop corrections may upset those limits. And we have to check that this does not happen. And that means that we calculated the loop correction to this mass matrix, especially focusing on the upper left corner, which is related to the corrections on the diagonal mass basis by this rotation with the matrices that I introduced before. Details are given in the appendix. Here I just put the formula because the calculation is actually not trivial, and it is quite amusing because it involves many delicate cancellations. And at the end, due to these cancellations, the result is very simple. This F matrix is given here. Otherwise, these are the masses of the vector and scalar bosons. This is the vacuum expectation value of the BH field. The vacuum expectation value of the second scalar appears implicitly through the masses of these vector bosons. And these Z and ZG and ZS 2x2 rotation matrices in the Goldstone and scalar sector. So as I mentioned, this result is gauge independent, finite, and as a result, it is also independent of the renormalization scale, so it is very well defined. And in fact, you can make an estimate of the elements of the F matrix. So these ranges are the ranges which the matrix elements take, depending on the mass of the vector or scalar boson in the loop. And of course, you have to take some example values for the masses of the neutrinos, the different ones for the left and right-hand side plots. What you can observe is that these matrix elements are quite large. You see here that the lightest neutrino assumed to be 0.01 electron volt, and the matrix elements can reach electron volt. So this might seem worrisome. But the coupling factors which multiply these matrices suppress the corrections significantly in what I call the super weak region of the parameter space. And so an estimate shows the corrections to the mass matrix. And if the active neutrino masses are order 10 to the minus third electron volt, then the corrections are 10 to the minus 7, so relatively suppressed by 4 orders of magnitude. The dark matter, let me now turn to the dark matter in this model. First of all, I mentioned the dark matter. We know that dark matter exists, but this known evidence is based solely on gravitational effect of dark matter on the luminous astronomical objects and on the Hubble expansion of the universe. Nevertheless, we know that the universe is filled with photons, with neutrinos, so it would be natural to assume that the dark matter has particle origin, and therefore you would like to identify this dark matter, but that is possible only if this particle interacts with the standard model particles, and that needs a portal. A portal which can be a vector boson, for instance, via the kinetic mixing that I mentioned before. It can be the Higgs or the scalar field if it couples to the dark matter particles, or it can be a neutrino if the dark matter is a fermion of dimension 3½ coupled to the HL operator, which is dimension 5. So together, this is dimension 4. And in this model that I'm advocating, the vector boson portal is the possibility with the Z prime, with the lightest sterile neutrino and 4 as dark matter candidate is a natural scenario. So if it is a scenario, then let's check it. And in order to check it, we have to recourse to the Boltzmann equation, which is used to compute the relic abundance. There are two possible mechanisms. One is the freeze in, and that means that the dark matter abundance increases from essentially vanishing initial abundance, but it never reaches equilibrium. You might ask why the initial condition is vanishing. That is kind of ad hoc assumption. And this mechanism requires very small couplings. Thank you. The other option is the freeze out, which means that the dark matter is in equilibrium with the other particles, but it decouples from those in the cosmic soup at some decoupling temperature as the universe cools. If the particle has mass m, they are in equilibrium with the others before decoupling, and the decoupling temperature is, as a rule of thumb, is 1/10 of the mass of the dark matter particle. And the decoupling physically is the result of scattering processes becoming very slow compared to the Hubble expansion. So simply they do not collide because they get very diluted. In the super weak model with the vector boson portal, both are possible. We studied both, but I'm going to focus only on the freeze out in this talk. The current exclusion limits on the Z prime vector boson portal leave room for masses above about 10-20 MeV. But if it is heavy, I mean several tens of MeV, then it can change the Big Bang nucleosynthesis dramatically through the production of standard model particles. And so we focus on a fairly small window, at most up to the muon pair production. So we cannot produce muon pairs. The dark matter particles are produced as a decay of the Z prime. So we need them at most 1/2 of this MZ. And we focus on the 10 to 50 MeV mass range. And if you take the 1/10 of that, it means that the decoupling temperature is order 1 MeV, which means that at decoupling, electrons, active neutrinos are abundant in the cosmic soup, but all heavier fermions are negligible. And with this assumption, you can use the Boltzmann equation to derive a differential equation for the so-called co-moving number density of the dark matter particle A. And schematically, this is the differential equation. So you have a creation of dark matter and an annihilation of dark matter. And this Z is the inverse temperature, lambda being some arbitrary mass scale. The rate itself is the cross-section or the decay rate multiplied with the available initial particle abundance. And these cross-sections or decay rates contain these K1 and K2, which are the Bessel functions of the second kind. And this also includes the cross-section, the scattering cross-section between the standard model and the dark matter particles. So if you solve that equation, this is the typical picture that you get. They are at some point before decoupling in equilibrium with the standard model particles. This solid line shows the solution of the equation. The dashed line is the equilibrium density, and the other horizontal line indicates the relic density corresponding to some parameter values. And you see that we can get, for instance, the correct dark matter density with 30 MeV of Z prime, 10 MeV of heavy neutrino mass. But this requires a coupling which is far too large as compared to current experimental constraints. So we have to decrease the coupling, but typically decreasing the coupling increases the relic density, and we cannot increase the relic density. So it seems that we are trapped, but actually we can increase, we can decrease the coupling, because if we observe that this sigma S contains a resonance, if the mass of the heavy neutrino is around the half of the mass of the Z prime, then there is a resonance here which increases the rate without increasing the coupling. In fact, you can decrease the coupling and keep the rate the same and keep the relic density as we want it. So the bottom line is that in the super weak model, it is essential that the dark matter candidate resonance can dominate the integral in the rate. And this is the parameter space. So these are the regions where we have the resonant contribution for different values of the dark matter mass. And you see that if you are not in the resonant region, then the model is not able to reproduce the known dark matter abundance, the relic density, but in the resonant region, it is not yet excluded by low energy measurements. So there is some room which can be tested. It gives actually a definite prediction, because the mass of the Z prime boson has to be about twice of the lightest heavy neutrino. Finally, I want to close that actually such heavy neutrino is not yet excluded, or in other words, possible if you take into account the neutrino constraints. Using the Kazasibara parametrization, the active sterile mixing matrix can be rewritten in terms of the PMNS matrix, the known mass, well, not the known, but the masses of the light neutrinos, the masses of the heavy neutrinos, and an orthogonal matrix. But actually, yesterday I learned by Pedro that there is a better way for this parametrization. So we are going to try that in the future. And knowing all these experimentally and we making assumptions on the values of M nu and MR, we can scan the parameter space of the R matrix to see whether we can get UAS such matrix elements such that they will be testable in future experiments. So these are the benchmark points that we found. 1 just examples. These are exclusion limits in the gray shaded area known today, and these are future experiments which will test this parameter space. So this is the U x squared, for x can be electron or muon, and I stop immediately. And on the horizontal axis, the heavy neutrino masses. And you see that these will be testable. In particular, the BP5 is such that it is also in the MEV range. The other ones are in the KeV range, which is relevant for freezing dark matter mechanism. So let me summarize. We know that the standard model works well, but we do not see any indication of very rich beyond standard model physics. This U1 extension along the philosophy of the standard model has the potential of explaining known results. We know how to fix the charges, how to generate the neutrino masses at tree level. One loop corrections do not upset it. The lightest sterile neutrino is a candidate dark matter particle. It can work in the freeze out case with definite prediction. It can also work for the freeze-in case, but I have not studied it here. We have valid benchmark points which will be testable in the near future, and I have not mentioned, but we have also paper on cosmological and particle physics consequences of the scalar sector, which is very interesting to explore further. Thank you very much.
Okay, sufficient.
Yeah, thanks for the talk. Can we go back to the second to last slide before the one before the summary? Yeah, one before, one after. Sorry, the plot exactly. So, what process is this which excludes this here at FCCEE? And what about other collider searches?
Oh, you mean what these are explicitly?
Yeah.
I don't know. I have taken these from the summary papers, and I still have to educate myself on this question. I don't know the answer.
Would be interesting.
Yeah, of course.
Thanks.
Thank you. This is a question for you and other speakers also. When discussing indications for BSM physics, I haven't heard any mention of muon G-2. So I'm just wondering why.
Okay. I can tell you my interpretation of the situation of G-2 at the moment. So there are two experiments which are not completely independent because the device is the same, but I still consider them independent. And they give consistent and very precise result experimentally. So I think the experimental side is well under control and will be better under control in the near future. On the theoretical side, there are two main predictions, and they are not compatible. Okay, one is the determination on the lattice, which is kind of close to the experimental result, not exactly on top, but within 1.5 sigma. So it cannot be considered as a very strong tension at the moment. Nevertheless, if you take the central value seriously, and in the future they can shrink the uncertainties, that will be some tension. The other one is where there is the 4.1 sigma tension, where when the hadronic contributions are extracted from experimental results. And I believe that people do their best to control everything, but today's message is that the theoretical predictions contradict. I mean, they are not compatible. So the theoretical community has to understand the source of this before we take this as a very strong indication of new physics. Actually, I have tested this model, whether it can, and of course, it can give contribution to the G-2 of the muon. It gives a positive contribution, but it cannot explain 4 sigma deviation. If I take seriously the lattice central result difference from the measurement, that I am able to explain, but I am not advocating it because of the current controversial situation on the theoretical side.
Okay, let's go last question. Yeah.
I'm not sure I understand what you mean by super weak theory. Super weak theories are in contradiction with the experiment. They are excluded. You know, main reason is because CKM matrix is proved experimentally to be a complex matrix. You know, super weak theories predicted that they were actually viable until the discovery of gamma. The gamma angle, the unitarity triangle, being different from zero, excludes all super weak theories. So what do you mean exactly? That I don't understand.
So super weak, I simply mean that the GZ coupling, which is the coupling of the new U1, is in the order of 10 to the minus fifth, or smaller.
Yes, but what the CKM, you know,
I have to
CKM is complex. In your model, CKM is complex?
Yes, of course.
Don't say that because you know super weak theory, CKM is real. The point, you know. The original, as you know, the original super weak model gives the idea that CP violation in K0 bar mixing is due to a new force that violates flavor by 2 units, and that immediately leads to a real CKM matrix. There will be nothing wrong, even with CP asymmetries, to have CKM real, but the discovery of non-vanishing gamma that proves that super weak theories are excluded, you know, as normally defined. If you have another definition, that's a different story.
Okay, so I'm not sure that we are talking about the same thing, but I have to study what you are saying and then see. Thank you. It's a useful input.
I'm just following the regular definition of it.
Okay.
Okay, let's further discussion after session next time. Let's go to the last speaker of this session, and he's online, Professor Sakar.
It's online.
Yeah, I'd like to share my screen, please.
Please, your talk 25 minutes to 5 minutes discussion. I'll give you 5 minutes, 25 minutes.
Right, okay. My talk is about PT symmetry and physics beyond the standard model. More generally, PT symmetry and field theory. There are some references here which are appropriate for the talk. And I shall give, because of the audience, I shall have to give also a bit of a review, and there'll be more references as we go along. So let's just, what's the context that that I want to put this talk in? So supposing we are working on a Hermitian type problem, and then some sort of non-Hermiticity comes along. Well, a traditional and completely understandable reaction is saying, well, the model we're dealing with is incomplete. And so, you know, other things that we've taken into account would eradicate that problem. But of course, we don't like non-Hermiticity because we think, well, that will not allow unitarity. So can we have unitarity? And if so, how? In quantum mechanics, there's been a lot of work on this, and the answer is yes. What I shall be talking about later on is, what about quantum field theory? The answer is less clear, but nonetheless, there are some interesting and encouraging signs. Okay, so how non-Hermiticity in terms of our general working, when we are working with kind of sensible Hermitian theories? Well, let's take a very simple example. Consider a two-level system, which is given by a 2x2 matrix. A, B, and G are real. If you look at the energy eigenvalues, very trivially, you can show that. Now you can see under the square root, there is a singularity, a square root singularity at a complex value. And these are called, in some of the literature, especially in the condensed matter literature, they're called exceptional points. And they are, exceptional points are so-called around in many systems. But also within a long time ago, there was work on the anharmonic oscillator by Carl Bender and T.T. Wu, and they had there again singularities in the complex coupling, which in their thing would be called the Bender-Wu singularity. But there are exceptional points in Bender-Wu singularities are of a similar type. So you can see that complex couplings do have a role in controlling how our theory can go. This is just one example. Now, in terms of the standard model and its extensions, especially the scalar sector, you've heard in this conference and in many other conferences, you've had effective actions which are in one loop, say, and they're of the form -5⁴ log phi squared. So this is related, people say, to the stability of the vacuum, and it's kind of falls off. So this has been known, and lots of people have been talking about that. Then also there is, in another context, supergravity in a Starobinsky type inflation model for inflation. There's dynamical breaking of SUSY, and there again, an effective model, effective potential has been calculated. And in the large field limit, where the field is the kind of F term in a chiral superfield, is given by -5⁴ log I phi. Again, these look in some ways to be unpalatable. So the question is, and you can say, well, okay, these are kind of one loop results and they're not the whole thing. And so, you know, we reserve judgment as to whether we should worry. But nonetheless, I'm trying to tell you in this talk that PT symmetry can deal with, potentially, with such potentials. And they should perhaps be of interest when we consider model building or other things when we go to beyond standard model physics. So let's go back to one of the kind of main Hamiltonians that have been dominating the PT symmetry literature. And this is a deformed harmonic oscillator. So you can see that epsilon equal to 0, you get the harmonic oscillator. And we know all about that. Now, but in 1998, Bender and Bocher studied this thing when you have epsilon not equal to 0, greater than 0, and less than 0. And they, in some ways, started the field off. And the interesting thing is that this model, although it looks non-Hermitian, has the symmetry that P, which I call P, a linear symmetry, x goes to -x, and then an antilinear symmetry, T, I goes to -I, are a symmetry of this Hamiltonian. So let me just give you a little bit of history here. When epsilon equal to 1, this model is Ix cubed. And I know that Carl Bender was telling me he went to Saclay, I think, and was talking to Zin-Justin, and they were saying to him, look, funny, we're finding this peculiar model, Ix cubed, and it's giving us real eigenvalues. What's going on? And so that question started off the interest in looking at such models. And so you can now actually do some calculations, whether they're numerical or by WKB methods. You can work out the eigenvalues of the theory here with epsilon being plotted along the horizontal axis and the energies along the vertical axis. And obviously at epsilon equals 0, the harmonic oscillators figure equally spaced eigenvalues. The interesting thing is that all the eigenvalues to the right, when epsilon is greater than 0, are all real. They're obviously not equally spaced, but nonetheless, the spectrum is real. There are no imaginary ones. And then, of course, as you let epsilon be less than 0, some of these things start coalescing, and then eventually they all disappear. And that's what is known, anything less epsilon less than 0, clearly we don't have real eigenvalues anymore. And we call that broken PT symmetry. So that's kind of rather remarkable. And it's something that you should bear in mind throughout the rest of this talk. So now you might say, well, okay, you've been lucky. You know, you've deformed the potential in that way. And so what about if I do something else and I got PT symmetry? So let me challenge you. Okay, so I've got x squared ix to the epsilon log ix. Remember, we've got lots of logarithms in some of these standard model effective potentials. Okay, and then we say, okay, let's rise to the channel. Let's see whether the PT symmetry is still going to do its job. And again, you can do this plot and you can see that they are remarkably all real eigenvalues. So you might say, oh my God, there must be something in this. But you're still, you know, so you begin to perhaps take things a little bit more seriously. And that's how I have to cut a long story short and say, well, hermiticity clearly from these numerical examples is not necessary for real eigenvalues. So what is the reason? Why do we get these real values? This is nothing to do with theory. This is just a numerical solution of a Schrödinger equation. And you get these answers, no arguments. Okay, so clearly hermiticity is not necessary for real eigenvalues. So what is? Okay, so what we are saying is that the Hamiltonians are they commute with PT, so they're PT symmetric in that sense. But there's an additional thing called a C operator, where C operator is such as an idempotent operator, which means that C squared is equal to the identity, and the C operator commutes with the Hamiltonian, and also the C operator commutes with the PT operator. And then if these C operators, if this happens, then you're going to get real eigenvalues. Now, C operators in general aren't that easy to calculate, but nonetheless, that's what the understanding is. That's what is replacing hermiticity. Now, let's look at some simple examples where I will just point out to you and explicitly show you a C operator. So consider the C operator is going to be of the form e to the q, where q is going to be a function of x and b, and then the parity operator p. So let's take the very, very trivial Hamiltonian, h equals half x squared plus a half p squared plus I epsilon x. There, the q is easily found to be minus epsilon p. Okay, let's take another example. Let's take the Hamiltonian to be a 2 by 2 matrix where R, S are real, theta is obviously real. And this is a PT symmetric thing where P is given by the sigma 1, the Pauli matrix there. And the Q you can work out, okay? And Q is in terms of the second Pauli matrix and log of 1 minus sine alpha over sine alpha, where sine alpha is related to the R's and thetas and S's of the thing. So again, these are calculations that you can do, and you can show, hang on, all of these things are fitting in with what the thesis that I said in the previous slide. So there is a whole body of work. There's now books written on PT symmetric quantum mechanics. And I'll just let you tell you that although I'm talking in terms of a fundamental physics, there's a huge industry in terms of condensed matter thing of doing applied research with PT symmetric things where they're having analogs of Schrödinger equations in terms of waveguides and paraxial approximation. And it's tremendously exciting work that's going on there. So PT has been having a lot of mileage in applied physics. So now to make a viable quantum theory, the eigenfunctions need to be orthogonal, and the C operator that I talked about is related to a replacement of the Dirac orthogonality. So instead of having psi star phi in that relation that we've got here, you have to have something different. And it's psi CPT, where the C, this is given by this, where this is our old friend, the C operator, which, as I keep on telling you, is not always easy to calculate. And unlike the Hermitian theories, you close your eyes when you're doing Hermitian theories. You say, oh yes, I know the inner product, and that's going to be psi star phi. But with the PT, it's going to be every theory may have a different C, and that's interesting, but slightly annoying from the point of view of theory, that we have to kind of, it's all self-consistently done depending on the theory. But we'll come to that as far as field theory is concerned in a moment. So if O is an observable, instead of having O dagger equals O, you have O transpose has to satisfy this theory. And this is, again, something which has been worked out over nearly 20 years now, I suppose, from 1998 to sort of now, over 20 years. It's been a large body of work which has sort of established this type of thing. So just in terms of, so far, I've just given you numerical work and others and things like this. And some of you who are more theoretical might say to yourself, oh, very empirical, isn't it? But actually, it turns out that certainly in the quantum mechanics case, there's been interesting work where you can actually work out when you solve the Schrödinger equation by the WKB method, you get two solutions: one which blows up along a direction, and the other which is falls off. And clearly, we want normalizable theories. So the things which fall off are called subdominant solutions. Now, these subdominant solutions are the things. So you want two subdominant solutions. One is x code for a large so-called positive real x and a large negative real x. You want two subdominant. To cut a long story short, you need to consider things called Stokes wedges. Okay, where you actually have to go and look at the paths in the complex plane. So the interesting thing about these paths is that this path here, the P of this path would be going along there. And as you then do I going to minus I, you jump down here. So that's why this is called a PT symmetric path. This has all been firmed up in a fairly pure mathematical and rigorous way by people, Dory, Dunning, and Tateo. And they've written a couple of other papers from Durham and whatever. And they have shown that this phenomena you can show is related to integrable models. And then they've done things in a rigorous way where they've actually shown that the spectrum is real in a certain class of models. But nonetheless, empirically, I've shown you that this is happening quite readily. Quite readily. So now let's go into quantum field theory. And clearly, if we go back to this quantum mechanical model that we have x squared I x to the epsilon. Naturally, in the scalar situation, you just replace x by phi of x to t. And so 1 for epsilon equal to 1, you get I g phi cubed. And if you got epsilon equal to 2, you get a minus quarter g phi to the 4th. And both of these models, as they were in quantum mechanics, are like anathema. We don't like them. But nonetheless, we're going to be, emboldened by what is being happening in the quantum mechanics. And we're going to try and see, hang on, what can we do with them? Now, clearly, you can have P as phi is a pseudoscalar. You have P phi is minus phi. P pi, which is a canonical momentum, P equals minus pi. All of this is kind of straightforward, and you can kind of work with that. But first of all, you say to yourself, "Oh my God, you are being very, very bold, aren't you? When you're in the quantum mechanics situation, you had to go for a C everywhere, every C, and you told me that it's difficult to calculate. Now you're going to take that step to an infinite degrees of freedom, and you're a very bold person. Have you got any chance of being able to do that? Well, that's part of your concerns are legitimate. And what I will try and tell you that no, although we are bold, hopefully we're not foolhardy. But before I go further on this, let's actually talk about a special solvable field theory model, which goes back. I mean, I think Steven Weinberg apparently worked on this model when he was a PhD student. So it's called the Lie model, okay? And it was written by T.D. Lee, among the many things that T.D. Lee has done, in 1954. And it involves spinless particles, but spinless bosons, spinless fermions, V and N, okay? And the reason why this model is sort of can be solved, because it can have infinite numbers of degrees of freedom. It doesn't have to be in a one-dimensional space or anything like that, is that you actually, because it actually, the Lie model doesn't have crossing symmetry. And so as a result, you have two conservation laws. The numbers of V and the numbers of N fermions add together is constant, and the number of phi scalars minus the number of N fermions is also a constant. So you have two conservation laws. And so as a result, you have superselection sectors, and you can certainly look at low dimensional superselection sectors where you can make a lot of progress. So we'll be saying, I'll just tell you the sort of results that you typically can get using the Lie model. And this is an example of a model where you can, you can solve it, at least with difficult, well, you have to work, but nonetheless you can solve it. Now, if you look at the relation between the Baire coupling, and I'm going to tell you the Baire coupling is the Yukawa coupling between V and N and phi, that's what the G is. I haven't written down a Hamiltonian yet, but I'm just telling you. Then if you work, you find that the Baire coupling G0 related to the renormalized coupling that we have here. If you go beyond a critical value of G, you get G0 squared becoming negative. So G0, you were an innocent man, or woman. You started off with the Hamiltonian and you had a G0, which was nice and Hermitian, and you said, oh, I'm happy, I'm dealing with something sensible. And then, renormalization, you get G0 becoming imaginary. So that's a ghost. And so for a long time, people said, well, the Lie model's sick. It's interesting, but it's sick. Okay, and that remained, it remained like that for a long, long time. And it was only after PT was kind of getting into its stride that there was some work done by Carl Bender and some co-workers, in which they re-evaluated this Hamiltonian. And here, as you can see, is the coupling that we have. And there's mass renormalization and all that type of stuff. And what they found is that this model, when G0 is imaginary, does have an underlying symmetry. And the underlying symmetry is just given by this, okay? This A is related to the theta. Theta, remember, is going to be something like A plus A dagger over root 2, okay? And as you go in the harmonic oscillator with X and B, and A dagger. So these are the sorts of things that you get. And these are all intuitively kind of straightforward that you have. And then it's a matter of algebra to show that this model here, where you had G0 being imaginary, so we have I mod G0, is actually PT symmetric. And now in this model, I don't want to go into technicalities, but these guys have done it. They've worked out the C operator. They found that in the new inner product, there ain't no ghosts. Okay, end of story, as far as they're concerned. So this was an interesting thing where PT has tried to make sense of a long-standing problem with theory with ghosts. Now, actually, if you go back again to an ancient book by Gabriel Barton, Introduction to Advanced Field Theory. In those days, dispersion relations and things like that were all the rage. People were trying to do non-perturbative stuff. They didn't want to do Feynman diagrams and all that. And so from dispersion theory, Barton had said that if you have an exact free vertex function, if you could calculate it, then if that does not vanish as K squared goes to infinity. Here you see P is coming in and then Q and K are going out. Okay, then that theory contains ghosts. So ghosts are not necessarily, in principle, they could be around. So So now we are got to the situation where I have indicated to you that that it's possible that PT theory, even in the quantum field theory context, is going to be interesting. But at the same time, I've also told you, and maybe perhaps a little bit nervous, and say, well, okay, this was an exactly soluble model, and you can work out the C operator and things like that. That's great. But what about the other types of models that you talked about? That could be very difficult, and that's surely a spanner in the works if you did something like that. Now, I'm going to say something here, which is that there's some work by Hugh Jones and Ray Rivers from Imperial in 2007 and 2009, in which they said that the C operator is somehow encoded in the, if you write down the partition function, a path integral, then obviously the paths themselves will have to reflect the nature of PD symmetry. But somehow they, by actually looking at Schwinger-Dyson equations and looking at Heisenberg equations and using the fact that the C operator on the vacuum is the vacuum. The vacuum is invariant under the C operator. They gave non-rigorous, but for people like me, moderately persuasive arguments, which said that no, if you calculate Green's functions, and I'm not talking about S matrix elements, because there you need to know the in states and out states and other sorts of things, and things can get a bit messy. We're talking about vacuum expectation. So within those type of Green's functions, then you can get away with not a priori calculation of the C operator. Wow, that makes me happy. And that's the reason we are trying to progress with this, saying, okay, we can calculate some limited things, but let's go ahead and try and do this. Now, the other thing, but that's fine, but clearly the things that I talked to you about in terms of the Schrödinger equation, I told you Stokes wedges, etc. That program of doing Stokes wedges and things like that is not an easy program to do within field theory. I mean, there is some work going on recently in things called Lefschetz symbols, because essentially what will happen is that for a field, for every X, you have to have a different Stokes path, and then you have to have a set of them, a thimble of them. I haven't actually studied that, but I think it's very, very difficult. So we've taken a more pragmatic, I mean Carl Bender and some of my other co-authors, co-collaborators. We've taken a point of view which is different, and we sort of say, well, we don't want to go down that route. We will take the path integral, and we will say that the path integral is somehow clever when we are calculating a la Rivers and Jones, when we are calculating Green's functions. And so when we've got something like this here, what we do is to say, okay, we're going to take the measure associated with the free theory, and we're going to do, instead of having a perturbation in G, we're going to have a perturbation in epsilon. Now, this type of thing has actually been done in kind of classical problems and solving nonlinear problems. This is called the delta expansion, and that's been developed over 20 or 30 years, but it hasn't really been applied so much, although a little bit has been done with Cooper and Bender and Moshe and people like that over the years, but not in a very systematic manner. So what happens is that you take this bold step of trying to do this expansion in this parameter rather than in G. And so you then get away, because of that, you get away from having to do the Stokes wedges and thimbles, which are exceedingly complex and bewildering, to write the theory in terms of polynomials, okay, but nonetheless polynomials where you actually, once you've actually worked out a Feynman diagram, you have to do something else, like take limits as n goes to 0 take derivatives, take integral transforms. So it's kind of there, but then on top of it before you get an answer. So essentially, for example, log of I psi is given by this half log psi squared times that. This can be written as the integral of 0 to infinity dt sine psi t over, okay, and you can then expand sine as a power of size, etc., etc. Log psi squared can be written as the derivative of respect to n of okay, logarithms come from derivatives with respect to n. This is used actually in the replica trick that is being used in spin glasses and disorder. So it's a kind of thing that is used in other contexts as well. So all this kind of stuff you can do, and then you just plow away. But before I say that, I will just say again, you can say, oh, you're being terribly bold again. Why should I believe you? Okay, well, that's fair enough. I'm not saying, you're wrong to be skeptical, but actually, if you look at d equals 1, okay, which is quantum mechanics, well, we can solve it by other means there, Schrödinger equation. So if you then work out the expectation value of the interaction Hamiltonian in the unperturbed ground state, you can work that out and you can compare it to working out in the partition function. You can work out the partition function using our expansion in these epsilons, and they agree. So all our cavalier way of writing down Feynman diagrams using this funny epsilon expansion that I talked about agree exactly. Okay, so certainly that is, well, that is something which makes us feel that, hang on, at least we've passed that test. So maybe hello? Okay. Hello. Right. So why are we getting this echo? Someone must be on. There shouldn't be an echo. Okay. So essentially, what we find is that when you do this, sorry, there is an echo. I'm not quite sure what's going on. So when we do it, we find that for d equals 2, so I'm sorry, has someone got their, are they unmuted? Someone else? Anyway, so essentially, when you do this epsilon expansion, what we found that we get 2-point functions, and we can get mass renormalization, we get expressions for the mass. But the peculiar thing is, and that's something we haven't fully understood, we find that higher order Green's functions, 3 and above, 3-point functions, 4-point functions, near d equals 2, they vanish. Now that could be, of course, you can say, well, look, you've done an expansion epsilon, which is kind of like the non-interactive limit, and so maybe it's just too weak. You're too near the non-interaction, and so you're not getting enough interactions when you are doing this expansion. But maybe. But what we've done is we've also tried to sum for each power of each term in the epsilon expansion, the leading order contributions, and you can sum the leading order contributions. Of course, we still find, unfortunately, that the 3-point functions and half-point functions still vanish, but in a much milder way. So it's possible that an improved way of summing the epsilon expansion could lead to something less trivial in terms of the half-point Green's function. But the interesting thing is that if you look at 3 dimensions, then you get none of these problems. They're all kind of finite sort of answers. So I'm just trying to say to you is that the jury is out. There seem to be a lot of intriguing features about these type of models. And let me just try and end by saying to you is that there are also people who are trying to build models. They're trying to write PT gauge theories and PT PT Higgs things, which is interesting model building. My point of view is that yes, we're going to certainly consider those type of models, but I'd like to make sure that we have some reasonable quantum calculations. They're not just kind of classical considerations of symmetry, interesting though they may be. The other thing I would like to say is that all of this is kind of scalar theory. I'm working with Nick Mavromatos and Alex Soto on kind of fermion aspects of these theories, and we're in the process of finishing some work. So clearly, for the model building aspects of it, eventually we'll have not only looking at the scalar sector, we'll look at the fermion sector as well. So thank you very much.
Questions? Online, we don't have questions.
I'm not.
I have one online. I'm Nick Mavromatos here. Can I ask it now?
Yes,
Okay.
please go ahead.
A very quick question, Shaban. The triviality that you get on the Green's function may be associated with the triviality of the phi to the cube theory, in the sense that you will have only a trivial fixed point, or
Well, no, but this would be true for all epsilon near d equals 2. It's not just epsilon equal to 1.
Right.
So
but maybe this means that this epsilon extended theory is trivial, or the method.
No, it may be that it might be dimension dependent.
It might be dimension dependent.
Yeah, it might be. Certainly in d equals 3, we get non-trivial results. Okay, but yeah. So the answer is it's not clear. It's not clear, but that's because it's very hard to sum up these epsilon things, because the diagrams and things become extremely complicated, and so yeah. But I do think though that there are probably other approaches as well, which we are thinking about in terms of these PT models. So the PT models themselves are not just hung on this type of technique. That's just one example of the technique, but the models themselves can be investigated, I'm sure, by other techniques, and they are they're interesting. So don't get kind of relate the technique to the general PT field.
Sure. Thank you.
In this session. Thank you very much.